all the 3 Nobel Prizes will be having a lecture here. So we had a lecture on these 3 Nobel Prizes topic. This year also we will be having the same thing. So we continue to have this. It is so PSL is a part of the Tamil Nadu Science Forum. I would welcome you all to become Tamil Nadu Science Forum and encourage you to be part of PSL. So PSL is predominantly run by the academicians, scientists, students, and the people who miss the opportunity to proceed their career in science. So all of you are welcome to join PSL, and we need a lot of people. So we also have a program plan to have a separate science movie sessions. It's going to be held here only. I'm in touch with the director of this library. Principally, he has agreed. We are looking for a good day for matching this thing. Maybe science, first the video maybe on the journey of man by Spencer Wells. So a lot of science videos are coming up, and we'll be having the discussion on the topic in the videos. It's going to be held once in a month. So it's that we are planning now. And Tamil Nadu, let me conclude with a little bit introduction about the TNSF Tamil Nadu Science Forum. It was a voluntary organization started in 1980 by the scientists and academicians in Madras University. So from 1980 it traveled a lot, and finally it has extended its arm to entire Tamil Nadu. So it is acting now. It is having 6 verticals. So basically, it starts with popularizing the science. Science popularization is one of the verticals. The second vertical is Science Forum is trying to bring women in science. So we have a separate vertical called the Samam, which give opportunity for women scientists and encourage women to get into science. The third one is we are publishing magazines, science publications. Fourth one is we are doing some research, and we are participating in the ongoing issues of the environmental issues. And we have a science for youth, a separate session. So these are all the verticals. So anyone can join in any of those things, and we can contribute. With that, let me ask Dr. Subhasti to introduce us.
Hello. Yeah. It's a very happy task to introduce Professor Ramaswamy today, and it's a proud moment to be part of Science Forum activities in this context. We're so interested in popularizing science, and I hope that you'll give more encouragement to these activities, all of you. If you don't mind, you could come forward, those who are sitting in the back, so that there's a lot of space. And having made that request, Professor Ramaswamy is a very inspiring person to talk to. He's very knowledgeable and all that. That's why I was very keen to bring him here for this lecture. He retired from Jawaharlal Nehru University, where he taught from 1986 till October 2018 in the School of Physical Sciences and the School of Computational and Integrative Sciences. From 1983 to 86, he was at TIFR, Mumbai. Between 2011 and 2015, he was the Vice Chancellor of the University of Hyderabad. Educated at Madras University, IIT Kanpur, and Princeton, Professor Ramaswamy's research interests have, over the years, been in aspects of theoretical chemistry, statistical physics, molecular dynamics, and computational and systems biology. If that's not enough, he's also a very prolific writer and has authored many books, including the first book of his that I read was the edited volume on Leelavati, called Leelavati's Daughters, which has biographies of 100 women scientists. It was the first of its work. I think it was in 2011 or something, 2008 that they published the book. I read it in 2011, and you can freely download this from the Indian Academy of Sciences website. He has mentored 35 PhD students at TIFR, JNU, in University of Hyderabad, and IIT Delhi. He has authored 200 peer-reviewed publications and edited over about 30 books, of which Leela's Daughters is the one I have appreciated the most. An elected fellow of Third World Academy of Sciences, of the World Academy of Sciences, Indian National Science Academy, New Delhi, and Indian Academy of Sciences, Bangalore. He served as president of Indian Academy of Sciences from 2016 to 2018. Currently, he is visiting professor at the Department of Chemistry in IIT Delhi. So I invite Professor Ramaswamy to comment, please.
Thank you very much, Shubha, and thank all of you for being here this morning. How do I change the slides, or do I ask you to do it? Okay. I requested Shubha to mention particularly that I had edited this book on women scientists, seeing the interest of the Science Forum on encouraging science in all sections of our society, including women. That's the usual way in which people state these things. I think, let me just make two statements of sort of regarding this particular issue. It goes without saying that the India that we live in today would not be possible without science, the methods of science, and our actual fundamental belief in the value and the validity of science. We may say all sorts of things, but the society, I mean, we cannot be sitting in a building in the 21st century of this quality if we were not fundamentally a scientific society. We have, we keep talking about the need for scientific temper and so on and so forth. That's all very well. But the importance of doing science and realizing that we are a scientific society should also go with the realization that we are systematically excluding many people, many types of people from contributing and participating in this endeavor. Even today, science is by and large an upper caste activity. Most scientists in India are Savarna. Most scientists in India, especially the leading ones, tend to be privileged males. So the value of bringing in different classes of people into science cannot be underestimated, both in terms of increasing the scope of questions that are asked and also in widening the kind of people who can contribute. This is a lecture in itself, so I will not proceed with that. I wanted to talk to you all about this wonderful world of ours. This is not to be a poetic lecture about, oh, what a great and wonderful world we live in. We do. We live in an incredibly wonderful world. However, what I'm going to do is I will keep a copy of my
that's just
lecture over here.
already correct. And the light up.
Right. The title that I chose was really to emphasize the complexity of the world that we live in. But nevertheless, I thought it was also useful to talk about the wonder that this world inspires in us. We live in a universe which is vast and a universe which is old. And we are beings without, this is just the facts. This universe, from the longest distance scales to the smallest distance scales, is something like 35 powers of 10. The distances within an atom are 10 to the minus 8, 10 to the minus 9 centimeters. And the size of our visible universe is some 30 orders of magnitude larger than that. 30 powers of 10. Or maybe even more. So, and time, from the beginning of the universe till now, and many of the things that we are interested in are on such short time scales. The range of times that we are interested in again spans a very large number of orders of magnitude. And given all this, the fact that I am here to be able to talk to you is the conspiracy of some very special circumstances. We are on a fairly ordinary planet at just the right distance from our sun, which is a fairly ordinary star. And this fairly ordinary star is one of billions which exists in our galaxy, the Milky Way, which is again a fairly ordinary galaxy. One of several billion galaxies in this universe of ours. We're just at the right distance, because much closer it would be hotter for life as we know it to exist. Much further away, again, it would be much colder for life as we know it to exist. The as we know it is important because our life is based on carbon. I mean, it's based on water, it's based on all sorts of various atoms and so on, but it's actually based on carbon. And the properties of carbon as an atom are so special that it is important that carbon compounds be stable at the kind of temperatures that which will allow life to evolve. What is a little bit of a coincidence in some sense is that I'm speaking to you after life has existed on this planet for 4 billion years. It's a little bit of a tautology. I could not have been here in less than something like 4 billion years or 3 billion years, because life had to evolve, cellular life had to evolve, multicellular life had to evolve, and the complexity of multicellular life had to evolve to give creatures like us. There is a sense of inevitability that, given the fact that you have life to start with, we will more or less come to the state of having, evolution will bring us over here, which is one of the reasons we do believe that out elsewhere in the universe, there is intelligent life. Because evolution is such a strong principle that it is impossible that if enough time has elapsed and if there is enough stability in the molecules constituting whatever goes into making life, intelligence is not something that would not occur. Right? Even though intelligent life, I feel, in my opinion, would almost certainly have occurred, we must acknowledge that other worlds may well be possible. And even for us, this means that even though we are unique, we are not exceptional. There will be other types of life. Of course, it may or may not look like us. It may or may not have all the characteristics that we assume or we take so much for granted about life on Earth and human life in particular. But there would be other beings, because, and this is the point that I want to make, that there is a complex evolutionary path that has been adopted, and if we are the result of one end of a complex evolutionary path, there are other ends and other beings and other worlds and other lives that would also have resulted. This is not a particularly new realization or even something that we've all realized after Darwin. There was a great philosopher who was given his name to a principle called Occam's razor. So William of Ockham, he was actually punished for this, but he gave lectures stating that God could easily make another world which was better than this one and distinct in species around it. So somewhere over there, the germ of the idea that we are not unique, we are unique but not exceptional, was there. Giordano Bruno had to suffer a little more, reminds us of the times that we live in. But he was burnt at the stake for many heresies, including the fact that there were other inhabited worlds. And one of the great scientists, in fact, the person who essentially started off science as we know it, Huygens, says, why should not every one of the stars and suns that we see in the firmament have as great a retinue as our sun of planets and moons to wait upon them, and therefore also perhaps to have life? This kind of thought has inspired poets. William Blake said, to see the world in a grain of sand and heaven in a wild flower, hold infinity in the palm of your hand and eternity in an hour, sort of capturing the fact that there are so many times scales that are important to us and so many distance scales. What I'm alluding to really is a very important principle termed the anthropic principle, which was first formulated explicitly in 1957 by Robert Dicke, who was a physicist at Princeton University, who said that there is a lower bound on how statistically probable our observations of the universe are, because observations could only happen in a universe capable of developing intelligent life. This is more than a tautology, because a universe capable of sustaining intelligent life had to be based on certain values of certain constants. If the speed of light were not what it is and was much slower, if light would travel at a slower rate, if Planck's constant, which is one of the fundamental constants that determines a lot of scales in the universe, were not as small as it was, we would just simply not have the right energies for molecules to exist. This is the anthropic principle, that the laws of nature, that the value of the gravitational constant is what it is. And the parameters of the universe, they take on values that are consistent with the conditions for life as we know it, rather than with a set of values which would not be consistent with life on Earth. It requires a little wrapping your head around, because this is not meant to be a trivial statement of we are here because we are here. This is saying really that the values of various constants, such as the speed of light, there are certain constants whose values don't matter. The value of pi, for example, that's an abstract number, and pi is pi regardless of whatever. But the fine structure constant, the value of, let's say, the speed of light, or Planck's constant, the charge on the electron, all these are very finely tuned. They could not be more than a few percent, not even a few percent. They're really very finely tuned in order to, in a sense, allow life to evolve. And therefore, that is the principle that all these constants are just the right shape and just the right size, so that I can be here and express thoughts. The principle states that this is a necessity, because if life were impossible, there'd be nobody around to observe it, and this would not be known. All right. My take from this is really that chemistry became possible because the values of all these constants are just right. Not because I'm in a chemistry department, right? But that's not the point. Chemistry became possible because all these values are just right. And that, combined with the fact that our planet is a special distance from the sun, says that chemistry, the chemistry on Earth, all the molecules exist on Mars as well, but the temperature is so low that many reactions slow down. It's just not possible for evolution to occur in the same way. On Earth, reactions are taking place at the right rates, right time scales. Things are happening in order for life to evolve. All right. Now, the last few years of our lives, all our lives, have been dominated by the pandemic. And we've become increasingly aware of the interrelatedness of many phenomena on the human scale. So I'm segueing into actually the rest of my talk, which is that we are here and this is a time for us to wonder. What is this wonderment due to? Because we are able to observe things and we are able to see things on a human scale. We are aware that, solid though this is, on a percentage basis, this is actually 0% matter and all of it is just empty space, as it happens, right? And if that doesn't fill you with wonder, I don't know what else will. But the problem is that we are observing things on a human scale, and we are also aware that you cannot keep on breaking things down into a smaller and smaller level, which has been the traditional way in which you do science. Break a thing, find out what it is, break what the constituents, find out what they are, and so on. Now, this has given rise in the last few decades to an area called complexity science. And over the years, this was a developing subject, but in 2021, there was a major boost to the field all over the world through the award of the Nobel Prize, not explicitly to complexity science, but to three people who were investigating various parts or various aspects of complexity. And I will describe some of those things as we go along. So, this was a moment in the sun for all the people who do complexity work. So one is sort of going to town on this. The awards themselves were to two people who were modeling the Earth's climate, and that has acquired a sort of urgency and importance in the last few years because of climate change. All of us are finally beginning to observe climate change on our time scales. Climate has changed over geological time scales. There is enough evidence of that in the Earth's record. But very few people will see climate change the way in which I think in the last few years we are all experiencing it. Every continent is having extreme behavior. Cities are having extreme behavior which we were not used to. I mean, the floods in Chennai is one thing, right? But the amount of rain, the floods are because of man-made interference. The amount of rain is indirectly because of man-made interference in the way in which we have altered the climate on our planet. People will tell you that North America is experiencing really phenomenally high temperatures for the summer. And so on and so forth. So one half of the prize went for modeling the Earth's climate to Syukuro Manabe and Klaus Hasselmann. They were modeling the Earth's climate, trying to quantify variability. The other half went to Giorgio Parisi, who is very well known in a variety of different areas in physics for modeling fluctuations and looking at disorder. So much of complexity science looks at order within disorder, because that is, at the end of it, the definition of what complexity is all about, and I'll come to that as we go along. Right. So complex dynamics, and the background is not just a pretty picture. Just one second, I just want to draw attention to the picture at the back. This is it's a print by Krishna Reddy, and it's called Turbulence. Turbulence, so you can see it's a wave visible to everybody with the structure of the. You can see that it's a wave, right? Okay. So this is an archetypical complex system because there is nothing regular or smooth about a turbulent flow. This is an example of something which is very familiar to all of us because we see turbulent flows all the time. In the morning when you boil a pot of water, you just look at it as it is bubbling, and that's got a lot of turbulence in it. So turbulent flows are archetypical complex dynamical system. And the idea about a turbulent flow is that you cannot predict very easily. Now, this entire discourse started with the discovery of what's called chaotic dynamics in the 1960s. Meteorologists were asking themselves a question. We know how the atmosphere, we know how a fluid behaves. We know how the atmosphere is a fluid, air, how that behaves. It is a special kind of fluid because it is heated at the bottom and it's cold at the top. Pretty much like a dish of water that you're boiling on your stove. You're heating it at the bottom and it's cooler at the top. So what happens? And when you started looking at this mathematically, it was discovered that the equations or these solutions have a property called chaos. Chaos, and I will try to explain it to you momentarily, is a way, as a mathematical term, it basically means trying to quantify how unpredictable a system is. Many systems are not chaotic, they are very predictable. If you go to your family astrologer and you take out a panchangam, or she'll take out a panchangam, and they will have a list of all the eclipses that are going to happen, and then they'll tell you don't go out, don't look at the sun, or if it's some lunar eclipse, they'll say don't eat that day, have 3 baths or whatever it is. But they know the time and the date of an eclipse very precisely, right? This is an example of a phenomenon that is complicated, but it is predictable. Because, if one goes today and asks, the they are going to give you a set of dates and times without any hesitation. But if you ask them what is the temperature going to be in Chennai tomorrow, or ask them will it rain or not rain, nobody, first of all, the astrologer is not going to tell you that, but even the scientific astrologer, otherwise known as a fluid dynamicist or a weather modeler or what have you, they're not always able to tell you precisely. They tell you that it won't snow in Chennai tomorrow, all right? But that's like a pointless prediction because it's not going to snow in Chennai. But so this is it. There was a very evocative example that was given by a famous physicist called Michael Berry. He said that the equations of motion of most things are so chaotic that if you had an electron at the absolute end of the universe, any uncertainty in the position of the electron would make the prediction of something over here as far away from the electron as is possible. It would make the prediction of this impossible after a very short time. I'm not going to read through that because it's there's some technical stuff. But basically, small changes in our knowledge or small changes, a little uncertainty in knowledge can give rise to huge errors in predicting, and I'll just explain what that is. So there have been, people have looked at models. Let's go to the next one. Right? There are 2 important models that have been developed, which have helped us over the years to understand a little about what chaos is. And I will try to, at least using one of them, try to explain it to you. Okay, for those who know what those differential equations are, or who know what a differential equation is, That's on the left-hand side. But I'll tell you what this system is. The Lorentz model is a very important model in the development of chaos theory. Lorentz was a meteorologist. He was actually trying to explain, trying to study the weather and model the weather. As I told you, the Earth, the air above our Earth is a fluid, and this fluid is heated from below and colder on top. If you've seen a pot of water that's boiling, and I presume everybody has seen a pot of water that's boiling, you would notice that there will be little variations in the density, and you can see that the water actually boils and moves around in, there are what are called vortices, but the water actually, when it gets hot, it rises to the top, then it turns around and it comes down, and this is how the water circulates. There are convection vortices. So what Lorentz was trying to do is to make a model of this convection vortex, and these variables x, y, and z are just variables that represent the pressure, the temperature, and the velocity, wind velocity. So this is an idea of what is going on. And obviously, if the velocity is moving around in a circle, this is essentially what creates a cycle. Okay. So modeling the atmosphere, worrying about the differences between temperature, this is a way of modeling weather. And Lorentz, if he had been alive, he died in maybe some things, but he's certainly one of the people who founded the field, so he should have or would have got the Nobel Prize. I mean, he had the prize as far as I was concerned a long time ago. Really fundamental work. Now, what is shown on this side is, after him, it's called the Lorentz butterfly. And this is basically, you start at some particular point, and then t is time. So you've got this variable x or y or z, and you just plot x or y or z along, as a function of time, you plot it on a graph. Right? And when you plot it on a graph, this is what it looks like after a while. I'll come down to what is important about it. Right? If you just plotted x as a function of time, you see that it has a very peculiar feature. For a little while, it's positive, then it comes down to 0, then it goes positive again, then it becomes negative, and then it oscillates, x going up and down as a function of time. This is a way of something just oscillating. It's oscillating negative, then it oscillates positive, negative, positive. And if you look at it, it has absolutely no pattern. It just keeps going up and down as you like. And just go back one slide. Yeah. So effectively, what's going on is that it's going around and around like this, and then it goes on this side for a little while, and then it goes on this side for a little while. So it's just switching apparently randomly between these two sides. Okay. But something more interesting was observed by Lorentz. If you started at this point over here with a blue pen, you trace out what happens as a function of time. This is just moving around, and eventually it traces out this blue trajectory that you see over here. But if you started ever so close, but not exactly at the same point, with a red pen, you'd go along for a little while, then you sort of separate from the blue and then swirl around and so on. And in the same amount of time, you started at blue, you end here. You started ever so close in red, you end over there. So very small differences initially give rise to very large differences as a function of time. Right? And this is a hallmark of what's called chaos, but this is also very typical of complex systems. We use it, we think about this all the time in our lives because the usual thing of appadi pannirundha, what would have happened? Or, if I had taken a step to the left or to the right, maybe things would be. We know this intrinsically to be true, that small changes at one time might have led to very large changes later on. This is a mathematical system, but it encapsulates the same idea that that small changes in initial conditions, and this is called sensitivity to initial conditions. Some systems are very sensitive to initial conditions and some systems are not. Those systems which are sensitive to initial conditions are called chaotic systems. If it is not sensitive to initial conditions, it's not chaotic. Right? And this is what makes prediction very difficult, or especially if you see that you started very close by, and with one trajectory you go to the left and another trajectory you go to the right. Where are you able to predict? Okay. Just go to the next slide, and I hope this will not scare you off completely. But there are. How is the maths in this room? Acceptable or not acceptable? Look, there is a certain requirement. You can't be a science forum if you are going to be afraid of math. This is not good. This is not possible. You have to be. I'm not asking you for go improve Verma's last year or something like that. I'm just asking you to stay along with me for a demonstration of what these. Okay, this is not important, but what I want to tell you is that the system doesn't have to be complicated. If we just go back a few slides, just go back one more. Yeah. You could turn around and say, of course, it's going to be sensitive to initial conditions. Look at the system; it's so complicated. That you think. For the maths unaware, that this might be a very complicated thing, and therefore you're finding this kind of behavior. The point is that the system doesn't have to be complicated at all. Let's just move on. All right, let's stop over here. Take a picture, look at it later on if you want, because this is just to say that even an equation which basically says take a number, double it, right? And whatever part is bigger than 1, throw it away. So if I take a number like 1/3, double it, 2/3, double that, 4/3. Whatever is bigger, so remove 1. 4/3 minus 1 is 1/3. 1/3. Double it, 2/3. Double that, 4/3. Right? So this is all I'm asking you to do. Take a number, double it, and whatever is, and take only the part which is bigger than 1. This is called mod 1. Right? So instead of 1/3, if I, just for argument's sake, supposing I took 3/4. If I take 3/4, double that, 1.5, right? 1.5, remove the 1, so you've got a half, double that, 1, remove the 1, 0, 1, 0, 1, 0, right? On 0, 0, 0, 0, 0, right? Okay. So this is all that, this is the game I'm asking you to play. So you notice that if I start with 1/3, I'll get 2/3, then I'll get 1/3, I'll get 2/3, and 1. Supposing I say that 1/3 is 0.33333333. So let me just take 0.33. Double it, 0.66. Now the error with the actual number is already, the error is about 6 parts in 1,000. Double that, I get 1.32. Remove 1, so it's 0.32. And my error is now 1 part in 100, because it's 0.33333 minus 0.32. So it's 1 part in 100. Double that is the error becomes 2 parts in 100. So see, 0.64 is close. This is what the error from 2/3 was. Then I get to 0.28. That's the error from 1/3. You can see the error is suddenly very large. And after 4 steps, I'm getting a number like 0.12, which should have been 0.333. And the error is just unmanageable. So it's all, so this is the power of this system. And such systems are called nonlinear. So nonlinear systems have the potential to show chaotic behavior. And this chaotic behavior is extremely important because we cannot predict it. Okay. Let's go to the next one. There was something more interesting about the system that Lorenz studied. He started at some point, and then as a function of time, he went on to this butterfly picture of his. He started at another point, and you reach the same butterfly. No matter where you start, at long times, you will always be there. This has been a very important notion that has come into science, and this is the notion of an attractor. That regardless of dynamics, there is something over there which is an attractor. And you start from somewhere, you'll go to the attractor. Start from somewhere else, you'll go to the attractor. That's why it's called an attractor, which means that in long time, regardless of other small details, you will always be at the attractor. Okay? Which is why, is there an attractor underlying our climate? It's a question to ask. Will our climate always be like this? Or, there are important questions that we would like to ask. I'm going to skip over the next few slides. Just go on. All right, just stop over here. This has actually, the fact that there is chaos everywhere. Oh, okay. As I told you, chaos is a property of nonlinear systems. Most systems in this universe of ours are nonlinear. There are very few things that are linear. By linear, I mean, as I was trying to explain, where you can predict very easily. One of the most common examples of a system which is nonlinear and unpredictable is this three-body problem. I know that there are non-scientists in the audience, so let me just very briefly tell you why this is an important problem. The first, our modern science essentially starts with Newton or Galileo, who were able to predict the motion of the Earth around the sun. And that is done if you just assume a massive sun and one Earth moving around it. If you put a third body, like, let's say, the moon going around the Earth and the Earth and the moon going around the sun, that system is actually not very easy to solve. What's worse is if you take Jupiter, put in the equation for Jupiter, along with that of the Earth, even ignore the moon, that is actually even today unsolved. You can solve it numerically, you can solve it practically, we can send Chandrayaan, Mangalyaan, Jupiteryaan, whatever yaan we can send, right? We can do these calculations, but you cannot get an exact nice solution like Newton did. It turns out that even the simplest problem of three bodies, that is the Earth, Jupiter, and Sun, is chaotic. And people use that chaos in order to get these planetary boosts as they move around and so on and so forth. So chaos is actually extremely important. And a typical orbit will, okay, let's go on. Many of just go to the rings of Saturn. Yeah. Some of you would have seen Saturn up in the sky. Yeah? At least you've seen a picture of Saturn. And one of the remarkable things about Saturn is that there are gaps in the rings. Yeah? Yes. This is a sort of a well-known thing. The gaps are the evidences of chaos. Because whatever was not, what is not there after so many years has certainly just gone away because it was chaotic. All right? And another example of chaos in our solar system is the moons of Jupiter. This is a moon of Pluto, but the moons of Mars are actually chaotic. They tumble around in a chaotic manner. So it's an important thing. Okay, now the thing is that one of the ways in which we see the evidence of chaos is in the structure of what is left behind. And for a long time now, long time being about 50 years or so, mathematicians and others have drawn attention to the fact that the world is actually filled with rather complex structures. We approximate things by straight lines and so on and so forth, but really the structure of very many common everyday objects is not at all describable in simple terms. So very poetically, Benoit Mandelbrot is a French mathematician. He said that clouds are not spheres, mountains are not cones, coastlines are not circles, and the bark of a tree is not smooth, and lightning doesn't travel in a straight line. We've seen lightning in the skies. We've seen images of various kinds of lightning. I'm pretty sure that everyone would have seen at least once something that looks, if not exactly like this, to a large approximation. It's important that the electric discharge from there to here is not in a straight line, because if it were in a straight line, every time it would just melt the earth at a particular point. Because it gets diffused out this way, you're able to, you're able to withstand some of these things. What Mandelbrot was talking about is that there is a property that we call fractality or scale invariance. You've heard this word fractals. People use it commonly, and even companies name themselves fractal and so on and so forth. But when an object has got structure within structure within structure, not simple like a plane, but something actually involved, this is what is called fractal behavior. What's shown on this side is broccoli. It's the Chinese broccoli or one of the varieties of broccoli. And you can see that what's over here, this floret, is repeated in each one of these. I mean, the whole thing is repeated in one, and so on. A mathematical model of what this is shown on the left-hand side over there. Within the big triangle, there are 6 smaller triangles. Within each of the smaller 6 triangles, there are 6 triangles. And within each of those, there are more, and so on. You can just imagine this thing going on to infinity, just downwards. So when you have an object where a part of it looks like the whole, this is called a fractal. And what this was for a mathematical audience. So we go to the next one. Okay, I'll leave this on while I tell you what a dimension is. See, one of the things that Mandelbrot was talking about was the fact that the dimension of an object is something that, without realizing it, we have a little, there's ambiguity in the way in which dimensions are discussed. Since this is a general audience, everyone is familiar with the idea of what is a one-dimensional object. 2 dimensions, yes. 3. Most of us can go up to 3 and be done with it. So a 3-dimensional object is, something like this. It's a three-dimensional object, right? Okay. Now, as far as you can see from a distance, this is a two-dimensional object over here, right? It's two-dimensional. If I were to be a little, what would you see? It's one dimension. Yeah? Okay. So, because you think there's only one important thing to vary along this side, over here there are two of them. But if you've got a whole three-dimensional object, you need to know various parts of it, right? Now, the problem about this notion of dimension is that it depends on the distance or the scale at which you are measuring something. Because if I tell you that this is a one-dimensional object, by the time I bring it close to your eyes, you can begin to see that there's actually a little more to it. So you can say, aha, at this distance it's beginning to look two-dimensional. And if I come even closer, begin to see that there is actually other extensions to it, so it begins to look three-dimensional. Then I ask you to shrink yourself. And when you shrink yourself and you're on the surface, what you see is just a flat surface, so you're back to two dimensions. You shrink yourself even more. You begin to see molecules, normally things all over the place. You say, aha, it's three-dimensional. You get even smaller. You think of yourself shrinking down to the size of atoms, and all you see are unconnected atoms all over space, which is zero dimensions. So the same object, depending on the scale at which you measure it, could be one dimension, two dimensions, three dimensions, two dimensions, three dimensions, or even zero dimensions. So dimension is something that certainly depends on the scale at which you measure something. Now, I'm not going to go into the mathematics, but Mandelbrot and others began to make us think about curves that were not one-dimensional or two-dimensional, but somewhere in between. They had a dimension which you could define, which is somewhere between 1 and 2, or 2 and 3, or 3 and 4, and so on and so on. Okay. Now these are sort of nice mathematical curves. As you can see, what you do is you start with a straight line, put a hat, then on each of those straight segments you put the same hat, and you just keep repeating it. Now the advantage of this is that if I take this entire curve and just look at this part of it and blow it up, it looks just like itself. And if I take this part of it and blow it up and blow it up, it's going to look exactly like itself. So this feature of something looking like itself over and over again is a feature that nature has used everywhere. And one of the most common places where it gets used is in our bodies. Okay, so let me just explain what the idea is. You see, the distance from this end to that end is, let's call that distance 1. When I do this construction, because I'm taking 1/3, you can see that the distance from end to end has become 4/3. When I go here, the distance from end to end has become 16 by 9. Small calculation that you have to do, because each one of these is 1/3 and there are 4 sections. Each one of these is 1/3 of 1/3. There are 16 sections and so on. To be able to convince yourself that from that end to here, the length of the curve is infinite. So getting a length of infinity within a box of size 1, you see the end-to-end distance is still 1. The curve has got size infinity. Right? Okay, there's a very, very important organ of our body where this principle is used. And just to make you feel that, make you understand that these are useful ideas. The amount I'm able to breathe depends on my lungs. But what feature of my lungs is important? Which is it?
Surface area of the
The alveoli is right, but what is the property, the geometric property that is required?
You want more surface to absorb.
You want more surface so that you can absorb more oxygen. Right? You're able to breathe, you would like to have a maximum surface. Now, if you took out our lungs, or not take them out, if you examine the lungs and looked at the area, that area is huge for anyone, right? It's huge. But I can't be walking around with some large body like that. Therefore, the design principle that nature has used is to make it tractable. You want a very large area in a very small volume. It's the same as having a very large length within a very small area. Right? So, our lung design is actually fractal. And one of the big problems of COVID was that it was making it less fractal. It was blocking up the alveoli, as Shravan has just pointed out. And it was sort of, it was making it less fractal, less efficient. That was a consequence. So fractal geometries are important. Not just for, you can get somebody to make a Mehendi design for you as a fractal. That would be good investment of money also. All right. We'll just move along a little. Yeah. It turns out that matter in our universe is actually distributed like a fractal. Obviously, we know that we are here on a single planet, but between us and the sun is a lot of space. Between the sun and other stars is also a lot of space. The way in which matter is distributed all over the world is as a fractal, and this fractal has got, there is a consequence as to how you would, what you're able to see because of this complexity. Okay. Go to the next two slides. Yeah. All this behavior actually has got simple origins. So, what I'm trying to tell you, or what is lovely about complexity theory, is that the origins of many of these things are not incredibly complicated equations that give rise to something that you would not only not understand, you would not want to understand. Very simple equations or very simple descriptions of things do turn out to have, turn out to have very complex solutions, and that's what I'd like to discuss. So one of the examples of complexity, or where this kind of scale invariance, or what fractals, etc., come about, is through the idea of a sand pile. Now, I hope all of us have played with sand. In some way or the other, we played with sand or picked up stones and thrown it at people. Some, you played with granular material of some kind, right? So now just imagine, or rice. When you want to pour out rice for whatever reason, you pour it out and it forms a pile, right? It forms a pile. So the sand pile is an example that has been used over the last 30 or 40 years to to try to understand the how complexity arises. I'm not going to go into that, but I want to just tell you that this is a simple system. What could be simpler than playing with sand on a tabletop or on a plate or something like that? So, trying to understand how systems like this organize themselves has been an important. Just move to the next slide. If you try to understand the physics of how sand will form a pile, this has been a very important idea. And I'll just allude to one property of a sand pile, which I'm sure you will remember. Going to the beach, you make a pile, regardless of whatever, so long as you don't put in water or pack it in somehow, the pile has a natural shape. If you add more material, it will just evacuate some of that shape and come back to the original shape. If it is below that shape, you can keep on building it up, and you'll always be at the stage where if it's like this, you can keep on adding sand, it will reach this shape. You add more, it will not support it. So the sand pile with a particular shape is just between, between these two stages. It's what's called critical in physics. But the point is just this, that a very simple system like this actually organizes itself. And it just stays at that level where a little more stress, it will crumble, little less, it will build up. The same idea applies to earthquakes, and that's huge consequences for us. All right, so there are these models that have been studied, and there's work that one has done at some point in time which has to do with these kinds of models. Let's just move on because this is not. I will just. All right, let's just go to the next Krishna Reddy picture. Like everybody who gives talks, I use the same talk in various different forums. So that was actually for another audience. So now, one of the most interesting features of complex system is an idea called emergence. And move on. One common idea of emergence is the idea of synchrony. If you've got a system which behaves in a particular way, and you put it close to another system of the same kind, you find that very frequently they go into a certain kind of synchrony. Right? This example that I have is a historical example. A man called Christian Huygens, he invented the clock, and he saw two clocks being placed next to each other. They were being wound so that they could keep time, and they started off at some arbitrary oscillation because these are pendulum clocks. But after a while, he saw that they were both going in sync or they were going out of sync. When you go out in the evening with your friends, regardless of your various heights, you pretty soon start walking in the same gait together. This is something that you notice people do, even if they've got some people who are saying, I'll go quietly, or I'll try to change the pattern. Inevitably, when you see four friends walking towards you, they've all got the same gait. That's called gait synchrony. This is the synchrony of pendulums, right? Okay. And go one more. Increase the volume. I'll just explain what this is if I have to. This is taken from YouTube. These are modern pendulums for metronome. They are on a common support, as you can see. And let me start it again. Right? They started off arbitrarily. And you can see that they are slowly beginning to communicate with each other. Perfectly in sync with each. Go to the next slide. All right, now what that is a demonstration of is, I mean, obviously one pendulum is by itself, there's nothing to say about it. two of them get into synchrony. But what you saw actually was a large number of them coming into synchrony. These are not animate objects. These are not people walking together who are adjusting their rhythms to one another. These are inanimate systems, and the state of synchrony is an attractor. Regardless of where you start, you will come to the state of synchrony. This is a very important sort of feature of.
Are the pendulums coupled in some way?
No, you saw them. They were located on the same swing.
But I see that the bottom base now it is making some.
Good observation, because that is what it is. Weak coupling, right? Obviously, if I take one pendulum here and one in Zimbabwe, they're not going to be in synchrony. They're sharing a common base, but there's nothing
platform itself is hanging.
But okay, so these are the features. What is it that creates this kind of, for want of, I'm not going to say it. What creates this collective behavior? Okay. This is an important point that people have realized in the last several years. That is that complex systems like this have a feature called emergence. The individual systems by themselves, they don't possess this property. It's only when you have large numbers of them together that you will find that systems have got a certain property, and this phenomenon is termed emergence. One of the characteristics of complex systems, and I've been trying to tell you different aspects of complexity, is that they have emergence, and examples of emergence are given over here. In large audiences, when people start clapping, sometimes you find that very strong rhythmic clapping that will start at some point in time. Nobody has told them to clap in a rhythmic fashion, but you just get tuned to it and you will synchronize. Right? There's a lot of synchronous activity in our brains, and many aspects of memory, etc., are to do with that. And here's an image of fireflies in Malaysia. These are male fireflies, and they all flash in response to each other. And you can see how, just do it again. First, there are a whole bunch of fireflies in a tree. Some of them sporadically go on and off. And pretty soon, you'll see the entire tree flashing. So they, if you go to Kuala Lumpur, they will take a lot of money and show you this. So, okay, in the next slide. But there's other phenomena that should also fill us with a certain wonder about this emergent property. So go ahead, please. So here's a bunch of fish. And you can see how, they start off randomly, but pretty soon, when they're in a school, they're all traveling together. This is another kind of synchrony that you observe. This is a spatial synchrony. The next slide shows you birds. Especially in England, you have flocks of starlings that are, a million strong. And these are, flying together. You can see the kind of complex aerobatics. They don't hit each other. They organize themselves into this really wonderful structure. This is called a murmuration. Right? And there's some interesting things to study about this, but this is another example of complexity. Now I'll show you two more recent examples of complexity. Just click on the right hand side or the left. Yeah. I could have easily chosen not to, although that was not really but I hope you saw what I was trying to illustrate over here. These two dancers, called the Gardner brothers or something like that, they're able to make a very something sort of pleasing and appealing to the viewer by exploiting symmetry, synchronization or anti-synchronization. You saw that at some moments their hands were in opposition, at some moments their hands were together, but both aspects of synchrony and anti-synchrony were exploited over here to create something. And then the other example over here is river dance. There are many things to talk about, but the point over here is that synchronization in space as well as in time are important emergent phenomena. Okay. And this brings us to what is complexity, right? So a complex system, to one or the other extent, shares many of the features that I've been talking about. You recall that I started with an idea of the dynamics of the motion is chaotic. It is unpredictable. It is sensitive to initial conditions. That was one of the features. Then that had a consequence. The consequence was that in a visible universe, we see lots of empty spaces. There's a structure. It's a well-defined structure. How does one analyze the structure in terms of its fractality, the way in which it is organized hierarchically, the complexity of that organization? Where does the fractality come from? It comes from fairly simple equations, simple properties of systems that give rise to this kind of complex structure. And a very important feature of complex systems is this idea of emergence. So over the last few years, our notions of complexity have become so sophisticated to say that, what is a complex system? It's basically a system that cannot be defined in terms of something simpler. Okay. The standard program of almost all of modern science has been to try to break things down into smaller and smaller and smaller entities, what's called the reductionist approach. If you want to know what is material made of, break it down. It's made of molecules. What are molecules made of? They're made of atoms. What are atoms made of? They're made of electrons and protons and neutrons. What are protons made out of? They're made of quarks, and so on and so forth. Okay. So each level we keep breaking it down. But knowing that an atom is made up of quarks doesn't tell you that it is, that a molecule is sweet or salty, or these are other properties that come about. So in some sense, if you cannot do reductionism to understand the properties that you are interested in, knowing all the molecules that are present in me, that everything that makes me up, will not tell you that I'm going to be rotating my hand around like this. Okay, this is another property which has to be thought about. Okay, so Giorgio Parisi, who got the Nobel Prize, had a very beautiful example, a beautiful definition of what is complexity. He said, the more you can talk about a system, the more complex it is. Okay, this is not this is a technical definition. Because if there is a lot to talk about a particular system, that means there are many variables, there's many things to describe, there are many parameters, and this is, in a fundamental sense, what is complexity. I've got a pen. if I have to describe it, I'll tell you it consists of two parts. Then there is a part which is sharp and there is ink inside, and I can put it on paper. And if I have to describe the computer, it's going to take more than 1 minute. It's going to take a long, long time by the time I describe all the parts, the way it works, and so on. So, to first approximation, the computer is more complex than a pen. And this can be quantified in a way in what's called computational complexity. But this feature captures the main property of complex systems, that in order to describe them properly, we need many degrees of freedom. And you have to sort of have these other properties, such as the most important one for me, next slide, is emergence. Many complex systems, in fact, almost anything that we would call complex, has this property of emergence, right? And this is something that a lot of people who work on complexity will agree with, is that it has, that the sum is, the whole thing is more than the sum of its parts. There is something beyond just the individual components, and that defines a complex system. Okay, the next one. Complicated does not mean, complexity and complicatedness are slightly different things. Things can be very complicated without being very complex. Okay, so there is a distinction to be made, and there are various mathematical and other physical approaches that people have used in order to describe such systems. But this is an evolving subject, and most importantly, it applies to the science of the world around us. You cannot understand the science of almost anything which interacts with the public at large without acknowledging the complexity of the situation explicitly. Because you can have a theory of how epidemics spread, you can have a theory of how it is transmitted from individual to individual, but unless you know how individuals interact with one another and other such features of it which make the system more complex, you cannot actually solve practical problems, as we discovered during the pandemic. Right? It was not a purely scientific problem, it was a complex problem. A complex in the way in which I'm describing. Okay, so let me wind down. Many systems are complex. We are all examples of complex systems, and these are complex in the sense that many different kinds of dynamical behavior are possible. That is one of the things about a complex system. We have different types of behavior, and in many of them, there's the possibility that small changes in initial states will lead to large changes in outcome. That is to say, that there is chaos. So complexity has as an ingredient complex dynamics, chaotic dynamics. This can be an advantage, because if you can respond to a small perturbation by a huge change, this means that you could potentially explore new behavior in responding to the environment. Now, fluctuations and uncertainty have actually played a fundamental role in the natural science. And we are the results of a very singular event 4 billion years ago, or 3 billion years ago. Life on this planet occurred, and it occurred once. I mean, the uniqueness of that event, it was a fluctuation, it was some sudden perturbation, but one must remember that certain events like this have been very singular, right? And the use of complexity science would be to try to approach questions like this, which lie at the interface of many sciences, many disciplines, which require the input of a variety of different kinds of specializations. That is what makes this field of complexity science quite interesting and applicable, and a big challenge. And with that, let me thank you for your attention. Next slide. Big bird? That's of course very good.
So let us have a quick question and answer session. Those who are having any questions, please raise your hand. I will give you the mic and we can have a question.
Broader philosophical question. I'm not yet sure of the right word for it. But this, the emergence phenomenon that we should take from order coming out of chaos in different situations, synchronicity. Does that reflect in a broader sense a propensity in nature for conformity?
What?
For conforming, for us to conform, to fall in line.
Well, okay, there are. I was giving you examples of spatial coherence and emergence in the on length scales, but emergence is even the emergence of consciousness, whatever that is. The fact that you've got groups of neurons in our brains that are firing together, or at certain intervals from one another, that underlies the emergence of something like intelligence or consciousness. And to me, I don't see the point of conformity over there.
Even in Fibonacci, for Fibonacci's patterns of nature,
Yeah.
do they point to something larger than that?
I mean, it's just the word conformity that that I'm not particularly happy about. You see, the emergence of these kinds of flocking behavior or order over there. This is a very simple reason why you don't want, you'd like to all be going in the same direction, that you don't hit each other. Alright, so there is certainly an element of conformity over there as such, but I don't see that as a driving principle. What I see as a driving principle is the avoidance of collision. If that makes it conform, so be it. Because, I mean, there are a whole lot of emergent phenomena where the words would have to be different. Yeah.
So you mentioned that you mentioned that nonlinear ODEs describe chaotic systems, but single pendulum is described by nonlinear.
It is a nonlinear differential equation. It is not chaotic.
So that act as a linear difference. So it's only generally nonlinear.
There are attractors in linear systems, nonlinear systems, and in fact, the only thing is that you have chaotic attractors only in nonlinear systems.
But the Lorentz attractor
is chaotic.
It's linear.
No, it's nonlinear equation. You're welcome to go back and look at it. They are nonlinear.
You take a three-body system like Earth, Moon, and Sun, or Earth, the Sun, Earth, and Jupiter. Where do we see this
Chaos.
chaos?
There are many examples of chaos between these things. One of them is that there is a famous point discovered by Lagrange, the Lagrangian points. In the month of August, that is this month, we will be passing through the Perseid meteor showers. Apparently, there was a planet somewhere over here, and that, because of instability, it fragmented and created what's called the asteroid belt. And when we go through the asteroid belt, it typically happens in the month of August. That is a very visible image that you see these meteoric trains. Big one? The Perseid meteor showers. That is because of, indirectly it's because of chaos. Yeah. Also the gaps, if there was no chaos, there'd be a continuous line of planets from the sun all the way out to Pluto. Whatever was unstable just went away. It had 4 billion years to do that, or more than that. they had some 8 billion years to get rid of all the chaotic stuff. And what we see today is just the remnants of what is stable. And those are the 9 planets.
Are these things will be stable further, or these things also can
Well,
unstable system?
this entire field started with a question posed by the King of Sweden. The King of Sweden in the year 1880 asked the question, is our solar system stable? And the answer to that is no. In general, the solar system is not stable. However, for the next few years, which is all that I'm bothered about, we will continue to be on the similar orbit for the next many years. We actually have an example of an unstable moon. The moons of Mars are unstable and they are slowly spiraling into Mars. Something like that could happen to Earth also. Okay, so that kind of stability, see, sometimes these questions are over what time scale are they unstable also. So if our solar system is unstable, our orbits are going to be unstable on some incredibly long time scale. Incredibly only for our own survival.
So, I have many questions, but I'm just going to ask you 2 more things. One is, you mentioned that the sign of, we are all basically a life made out of carbon.
Yeah.
But when these guys look for signs of life outside, they look for nitrogen. Why is that?
That's for metabolism. The product, we need carbon to form our structure, but we also take our energy from different, from different molecules, ATP, ADP, and so on. So if there is metabolism, which is going to give us energy, that is going to be based on compounds of carbon plus oxygen plus nitrogen plus phosphorus and so on and so forth. Okay, so it's going to have a complex chemistry. And then what you look for is long-lived isotopes. Nitrogen is one of the longer-lived isotopes. That is the reason.
The other question is, there's this distinction between simple systems and complex systems. And then you also mentioned the reductive way of studying, which is physics way of studying in some sense. Biologists are not very happy with this because they study.
There's a whole field called systems biology that came up in the last 20, 30 years. Because, knowing every molecule in me doesn't say why I can walk or talk or take a bird. The bird is also made up of exactly the same molecules as you and I. Yet that thing can fly and you and I can't. Right? Why? So we need to understand things at a system level rather than at the, breaking it down to smaller and smaller bits.
So my question is, with the complex systems approach, can you model a biological system?
Any kind of modeling in biology is done through complex systems approach. There are different aspects of it. I think these are a little more technical and more complicated, but many methods of studying complex systems do apply in biology. Not always to answer the most interesting questions, but
The unpredictability of the earthquake.
Yeah.
Is it due to chaotic phenomena or lack of knowledge?
both. I will amplify on that and please say this.
Thank you for your very difficult speech. I am Srinivasan, sir. Time, space, and distance. The distance is measured by the astronomical unit, years. And then your time you have measured the orders of the magnitude. Is the what's the scale of exactly?
See, the shortest reactions, etc., that take place, that we are aware of, are of the order of 10 to the minus 17 seconds. 10 to the minus 17 seconds is the typical atomic time scale. And the age of the universe is something like 15 billion years. Right? So if you convert that into seconds, that will be 10 to the plus 20 or 30 or whatever it is. I did the calculation to write down 35 orders of magnitude. So the smallest, the fastest things that we observe as humans is about 10 to the minus 17 seconds. The longest time scale that is present to us is the age of the universe.
I think it's not about the distance, right?
Both of them.
Distance is measured in astronomical period.
Yeah, distance again going down to the size of the nuclear size all the way to the edge of the universe is some 40. Let's say, typically both of them are 40 orders of magnitude.
And then the space, how to measure? To my understanding, space can be measured by the constellations, planets, and then the stars. Or any other
Mr. Srinivasan, I was just talking about the physical distance, measured in centimeters, if you like, from here to the edge of the universe. I wasn't looking at it in terms of stars and so on.
But without understanding, when you're talking about time and space, you have to make some way of understanding method, to understand. Again, talking about space,
Okay. See,
to understand.
the point that I was trying to make is that the physical universe that we inhabit has got phenomena that are occurring on time scales that go from 10 to the minus 17 seconds to the age of the universe. There are events and phenomena that span all these. There is also spatial phenomena. What's the size of things? So the size of things goes all the way from 10 to the minus 8 all the way to the edge of the universe, which is 10 to the plus 42 or whatever it is. Okay. So the world around us has got a huge range of phenomena on both these scales, and is therefore something that fills me at least with wonder.
Sorry, you also mentioned complex physical system, what exactly it means physical dimension?
No, I was trying to say it has complexity in its behavior. So small variations will lead to large changes. It has complexity in its structure. It's typically fractal or hierarchically organized or what have you typically. It shows emergence, but it could be described by a very simple equation. Okay, so that they are not complicated, but they are complex.
Times a couple of years back, the number of stars of Newton was shouting towards it because I used to sit on momentaries for long hours, 2 a.m. like that. And I just so bad.
Sure, it will have an adverse effect on human beings if it hits you on the head. If it hits you on the head, you're gone.
It's
It's a large one. No, most of them burn up entirely in the atmosphere. So, yeah, and see, I mean, the meteor is just a stone from space. It also contains carbon, iron, it's also made up of exactly the same material as stones are made up on Earth. So, depending on the size of this rock, if it happens to go through you, that's curtains. But there is nothing, I mean, it may be extraterrestrial, but this is not some mystical object. So nothing to worry about that.
Now I have a question from YouTube participant.
Sure.
The question is, thank you very much, a very exciting talk, a very basic concept of science explained in a simple way. Question, whether the phenomena of human consciousness is an emergent phenomena?
I actually alluded to as much that it's pretty clear that the neuron has evolved in varieties of different organisms. The smallest worms have got neurons. Many organisms have brains. But there seems to be some step that we don't understand between having neurons that communicate with one another, that act together, and a slightly higher level of behavior that we call consciousness. It's not that humans are the only ones that have consciousness. I'm pretty sure that a variety of mammalian species have something that we would have to call consciousness. Right? But this is not something that a single neuron possesses, or even a small number. think that there must be some kind of a threshold above which the architecture, the communication, all that going together gives rise to what we call consciousness.
Right? Any questions?
Sorry.
Almost. Thank you very much. Who is going to have the time? Thanks. All right. Let's start with the very last thanks for up. I have to play all the roles, introducing, thank you, all these things. Right. So it's a formal thank. Thank you very much, Professor, for accepting this lecture, and it is a wonderful lecture. So I would like to have one more lecture on emergence. Science Forum has already done a lecture on emergence, and we also have a lecture on Paris' work. Both we have conducted, and we would like to have one more lecture on emergence. It's an interesting topic which is coming up. So thank you very much, Professor. It's
My pleasure.
Wonderful talk, and I would like to thank all the audience for the participation, and be patient and actively participate in the session. Thank you very much for the audience, and thank you very much for the library authority for providing the hall and make arrangements, and they provide the AC, all the infrastructure. Thank you very much for that. Particularly my thanks goes to the director of the school education, Dr. Mahawat, who is very much interested to organize such lectures in this library. And I would like to thank my friend Sundar, who is always the technical person behind the event, and he's broadcasting this. A lot of people are attending in the YouTube. It's going to be permanently in the YouTube. Anyone can see in the YouTube, and we have a YouTube channel. Become a member of YouTube channel and access all the 62 lectures. We have all the lectures in the YouTube. Finally, I would like all the audience to become member of Science Forum, Tamil Nadu Science Forum. We have our WhatsApp group, we have Telegram, and we also have the Instagram, right? We also present in the Instagram. All social media we are there. Please track it, and you can be a member of a WhatsApp group. You can be a member of a Google group as well. You can be a member of Tamil Nadu Science Forum, and I would encourage you to participate in the future lecture, and I would invite you to become part of the executive committee of Popular Science Lecture as well. Thank you very much.